So we've drawn a series of structures last class session, and one thing that we may have noticed is that your proposed Lewis structure may not have been exactly the same as your instructors. Now, this is because you can end up drawing structures with the same formula in which the atoms are bonded in a different arrangement or connectivity, and we call these structures constitutional isomers. So for example, CH3CN has multiple plausible Lewis structures, each representing a constitutional isomer. So CH3CN, or acetonitrile, can be written out, one possible Lewis structure looks something like this, right? This is probably the most common structure for acetonitrile, where this functionality is known as a nitrile. However, we can just as easily rearrange the connectivity of our atoms, and we can get the not so pleasant to handle relative of the nitrile, which is known as an isonitrile. Does everyone notice how these structures have the exact same formula, but the connectivity is substantially different? Does everyone see that difference in connectivity? So these two isomers are constitutional isomers. They have the same formula, same number of atoms, same number of electrons, just different connectivity. You can even get a little bit more adventurous and draw some quite interesting constitutional isomers. So for example, this structure below is also a constitutional isomer. So with some creativity, you can draw a range of constitutional isomers. And it's important to be able to recognize constitutional isomers because they're quite common when you're looking at products from organic reactions, especially if you lack regiospecificity. So this is a big one. Structures with the same formula in which the atoms are bonded with the same connectivity but a different 3D shape are called stereoisomers, different shape. So what do I mean by that? Well, I can show you a model. That'll be one way of showcasing it. So let me make a model really quickly and I'll turn on my camera and show that to you. So dibromoethane. So BrC2H2. So there are two possible ways we can draw this structure. We can either have the bromines on opposite sides of our double bond. We call this the trans isomer. Or we can have both of our bromines on the same side of our double bond. We call this the cis isomer. Now, to really help us see that these two molecules have different shapes. So if we look at the trans isomer, I'd like you just to take in and appreciate the shape of the trans isomer. Does everyone notice how the bromines are on opposite sides of our double bond? Does everyone see that in our model? Okay, now I'm going to show you the cis isomer. And I'd like you to tell me, is the shape, the three-dimensional shape and position of our atoms the same or different? So here's our cis isomer. Is it the same or different? It's different, right? Now we have both the bromines on the same side of our double bond and the shape of our molecule is now changed. So stereoisomers have the same connectivity, same bonding order, same bonding connectivity of our atoms, but they have a different three-dimensional shape. Other examples of stereoisomers that we'll see later on in this course. Other examples of stereoisomers that we'll see later on in this course has to do when we have a carbon with 4 substituents. Now, when we look at these two structures, we have the same connectivity, but these two molecules have different shapes. So you can also end up with stereoisomers, not just for alkenes or not just for double bonding arrangements, but also for tetrahedral centers. We'll talk more about this in chapter 5. Okay, so constitutional isomers. You really want to make sure your constitutional structures have a different bond connectivity. And make sure you're really paying attention to rotation and other ways of drawing the exact same molecule. For example, which of the following structures are constitutional isomers? Now, you really have to draw all of your molecules in the exact same way. So I'm going to set it up so my molecules are all drawn out in as close to an identical way as possible. And worst case, I'm going to number my carbons. So number 1, 2, 3, 4. Okay. Number 1, 2, 3, 4. Number 1, 2, 3, 4. To make it a little bit easier to see, and this is where your model kit's invaluable, what we're going to do is we're going to rotate this molecule so that we can draw it in a slightly closer format to our other molecules in this list. Now, my question to you is, when we look at A, B, and C, which structures are constitutional isomers, as in they have the same formula but a different connectivity? They're pairs. So B and C, that's a very interesting idea, and we do want to talk about that actually. So if we look at B and C, do these structures have different connectivities, or are they the same molecule? And to help everyone see that, let me make a model really quickly. So if we think about let's try to think about that question for a moment. Are B and C the same molecule or different molecules? So are B and C the same molecule or different molecules? Yeah, B and C are the same. And so just to showcase that, let me show you a structure. Let me show you a model of B. Okay, so here is our model of B, right? Now, without changing anything, I'm just going to rotate this molecule, and lo and behold, do we see the structure for C? Via rotation, do we now see the structure for C? Yes. So then, you really need to be careful for structures that are just rotated versions. So B and C are identical. However, if we look at our carbon numbering, which pair of molecules are constitutional isomers? Same formula, different connectivity. Which structures are constitutional isomers? Which set? A and B, yep. A and B. That would be a set of constitutional isomers. You can also just as easily say A and C are constitutional isomers because they have the same formula, but a different connectivity of atoms. Does that make sense? Any questions on this idea? If not, let's do some practice. So we're asked to draw at least 2 constitutional isomers for the following formula. So we have C3H5NO2. Okay, I'm going to count my electrons. So for carbon, we have 4 electrons and we have 3 carbons. For hydrogen, we have 1 electron and we have 5 hydrogens. For nitrogen, we have 5 electrons and we have 1 nitrogen. And for oxygen, we have 6 electrons and we have 2 oxygens. So adding up our electrons, we get 34 electrons total. And there are a range of possible constitutional isomers that we can draw. I'm going to draw out my skeleton. This NO2 is a common functional group known as a nitro group. So I'm going to try to keep that together if I can. So I'm going to form 1 bond each. So we have 30, and I'm going to include my hydrogens. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 14 electrons remaining. I'm then going to place lone pairs on my outer atoms. 2, 4, 6, 8, 10, 12, 14. We're out of electrons now. And then we're going to fulfill the octet rule by forming bonds from our lone pairs. So this gives us the following first structure. And now my question to all of you is there a way for us to rearrange this structure to generate a constitutional isomer? Well, there's actually a nice little trick that you could use. So what you can do is you can pick 1 attached atom or functional group on each of our 2 carbon atoms. So if this is 1 and this is 2, I'm going to pick the hydrogen atom and this nitro group. And now all you have to do to get a constitutional isomer is you swap the position of your functional groups. Now, in order to avoid accidentally assigning and drawing out the exact same molecule, we're going to use one more counting method. So we're going to number our carbons in one direction and then number our carbons in the opposite direction. Now, as part of this rule, as part of this guideline, you're only going to want to swap your functional groups if they have different numbers in both of the counting methods. Okay, so if we swap our 2 functional groups, we end up with the following structure. And now, if we look at the connectivity of our functional groups, are these 2 structures constitutional isomers? Do they have the same or different connectivity? Do these structures have the same or different connectivity? Different, yep. So these 2 structures would be constitutional isomers. You can just as easily swap other functional groups as well. You can just as easily swap the methyl group and the hydrogen. Sure, that would also work. That would be another way of drawing constitutional isomers. So one question that sometimes pops up is, what happens if I want to swap my carbon and this nitrogen? So if we number out all of our atoms, one thing I'd like you to pay attention to is what are the numbers for the nitro group and this methyl group? If we count using both of our counting methods, are the numbers the same or different when we count from left to right and right to left for the nitro group and this methyl group? Are these assignment numbers the same or different? So if we look at the number in blue and the number in red, they're the same, right? So even if you wanted to swap these two groups, you wouldn't actually end up with a different structure. Likewise, this is the same reason why we can't just swap our hydrogens. This is the same reason why we can't just swap our hydrogens, because their counting numbers are the same. If we swapped our hydrogens, we'd end up with the exact same structure. We'll see more examples of this numbering shortcut, but in general, if you're ever unsure, just draw out the structure and number your carbons, and you'll notice that the carbon numbers are different in constitutional isomers. There's a different connectivity to each carbon. So for example, in this structure, if we number our carbons and nitrogens, we notice very clearly that carbon 2 has different substituents attached to it. Yep, so our counting numbers have to be different in order for a swap to generate, a constitutional isomer. This is a common shortcut just to help keep things organized and to remind everyone to number their carbons. Does this make sense to everyone? You don't have to know this shortcut in detail. This is just a way of checking your work. Now, I'm going to show you a trick to draw constitutional isomers quickly. Now, you don't have to memorize these bonding motifs, but since we know the bonding preferences of neutral and charged atoms, we can draw a series of, yes, I find it easier to look at the functional groups and then swap their positions if they have different carbon numbers. Yeah, that's the method I prefer, as it's much more procedural. So continuing on, we have different bonding motifs for our neutral, cationic, and anionic species for each of our atoms. So we have each of these single bonded motifs. I've also provided a list of double or triple bonded motifs for carbon, nitrogen, and oxygen for neutral, cationic, and anionic species. Now, the reason why I'm providing you these bonding motifs is that most organic compounds are represented using condensed structures and condensed formulas. And from condensed formulas, the arrangement of atoms can be determined, and it makes it very easy to find and to identify these different bonding motifs. So, what are condensed structures? Well, condensed structures, there are two major types. So we have partially condensed structures, where rather than drawing out all of our carbon-hydrogen bonds in our Lewis structure, instead, what we do is we omit and we do not explicitly draw out our carbon-hydrogen bonds. So this structure here, without the carbon-hydrogen bonds drawn, would be a partially condensed structure. Now, in a fully condensed structure, all carbon-hydrogen and carbon-carbon single bonds are not drawn. All other double bonds and double bonds associated with carbon, as well as triple bonds, are drawn. Now, the nice thing about condensed structures is that they clearly indicate functional groups in a molecule. So a functional group is a specific group of atoms with unique reactivity. And you're going to want to be familiar with the formulas for different functional groups. So now that we've seen what condensed structures are, we'll unpack how do we write them, how do we unpack them, and how do we draw structures from condensed structures. So alkanes are just carbon-carbon single bond containing structure. Alkenes have a carbon-carbon double bond, and alkynes have a carbon-carbon triple bond. There's one other functional group that you're going to need to be familiar with called an arene. In this case, we have alternating single and double bonds in a 6-membered ring. So this functional group is known as an arene. And if we're looking at a very typical arene, this functional group here is known as a phenyl functional group. So we're now seeing our first set of functional groups, and you may ask, well, how are these functional groups represented? In condensed formulas, you will see explicitly the double and triple bonds drawn. Another signpost you're dealing with an alkene is you see a CH double bond CH functionality. Alkynes are indicated by the fact you have 2 adjacent carbons with no hydrogens attached. So we've seen these functional groups now. Let's look at an example of how these functional groups appear in structures. So I provided you a list and a table of different functional groups along with the oxidation number for primary, secondary, and tertiary carbons. This portion of the table will come into play a little bit later on in the course. So for now, let's just look at some of our functional groups and let's talk about some interesting features of these functional groups. So an alkane, so we just have carbon-hydrogen single bonds, and its condensed formula is of the form CnHn+2. The name ends with ane, so alkane names are ended with ane. For cycloalkanes, the main difference and the main way you can tell that you potentially have a cyclic structure is that we have 2 less hydrogens, and the name is of the format cycloane. Alkenes, as we've seen, has a condensed formula, again, very similar to our cycloalkane of CnHn, but in the condensed formula, if we have an alkene, we'll be able to explicitly see the double bond. The other hint is in the name, we'd see the -ene ending. Finally, alkynes, which have a carbon-carbon triple bond, again, we'll be able to explicitly see, we'll be able to explicitly observe the carbon-carbon triple bond as part of our condensed formula, and the name ends with -ine. There are a few other functional groups that I've provided for you that I would recommend that you familiarize yourself with. These functional groups show up a ton in organic chemistry and will often be seen in this next chapter on acid-base chemistry. I've also provided you a table of carbonyl and other related functional groups. I'm not expecting you to memorize these immediately, but you should start looking over these functional groups, becoming familiar with these functional groups, because it really provides you the tools to shortcut in drawing out your structures. If you can identify your functional groups, it makes it a lot easier for you to draw out and to expand condensed structures. So let's unpack condensed structures. So first and foremost, if the portion of the formula has a subscript, the subscript indicates the number of formula units attached to the carbon chain. Okay, so for example, CH2 subscript 2 tells us we have 2 CH2 groups attached to each other. Does that make sense? Okay, so a carbon containing a functional group or attached formula subunit will have less hydrogen atoms than an unsubstituted carbon. So I'd like you to pay attention to this boxed carbon. The arene will have a different number of, the arene 1 has a defined number of carbons. That's a 6-carbon cyclic structure. And the arene also has explicitly noted double bonds, or the aryl group is denoted by a unique symbol. Does that make sense? And further, if you're curious, so if you compare a cycloalkyl group to an aryl group, the aryl group has the formula CnHn, while the cycloalkyl group has the formula CnH2n. So the cycloalkyl group has more hydrogens as well. Now, this is actually very closely tied to this discussion, because if we pay attention to this carbon here, we have 2 things attached. We have 2 things and our main chain attached to it. Does everyone notice how this carbon just has 1 hydrogen? I'd like you to compare that to this carbon here, where it's just attached to 1 functionality, and as a result, it has 3 hydrogens. The carbon with side chains or functional groups attached to it will have less hydrogen atoms. Now, the reason why this is important, is because, and this is really key, whenever you observe a functional subunit or a functional subunit after a carbon, if that carbon has less hydrogens than a typical straight chain alkane, then the groups indicated in parentheses are attached to our carbon. So we denote the fact we have 2 methyl groups attached to this carbon using the form CH3 In this case, these methyl groups, these CH3 groups, are attached to this carbon. And just to repeat, how can we know that? How do we know that? What's special about this carbon? What's special about this carbon? What did we note about this carbon?
It has 1 less hydrogen.
Yep, exactly right. And that's a signpost. There's something attached to our carbon in place of a hydrogen. Perfect, perfect. So this would be a partially condensed structure, and then we can condense our chain further by noting the fact attached to this CH functionality, we have 2 of our CH3s or methyl groups. Does that make sense to everyone? So we can both abbreviate our chain using subscripts, and we can abbreviate the number of functional groups attached to one of our carbons. Now, in general, when you see these parentheses, you immediately want to ask the question, is this attached to my carbon? And the way that you can tell is by looking at the number of hydrogens attached to each carbon. So let's look at another example where we can get even more fancy. So we don't just have to have methyl groups here. We can also attach other functionalities. So reading off from this condensed structure, I'm going to write a CH3. Okay, then I'm going to write a CH2. Okay. Now, what do we notice about this carbon here, this carbon that I put a star next to? Does it have
No hydrogens.
What was that?
It has no hydrogens.
Exactly right. So then it must have something else attached to it. And since we see these parentheses are indicating to us this group may be attached to our carbon. And because our carbon has less hydrogens than usual, this functional group, this functionality is attached to our carbon. So we have 3 of these CH2OH functionalities attached to our central carbon. And that is the only way for us to have a valid structure that fulfills the octet rule on this central carbon. Does that make sense to everyone? And the reason why I drew 3 of these functional groups is because what is our subscript? What is our subscript? 3, yep. Now, likewise, just to elaborate on another use of subscripts, if a formula unit is repeated, it can be abbreviated using a subscript. So as we notice, both of these carbons have the proper number of hydrogens for a complete octet. So it looks like this CH2 group is just representing a chain. So then, because we have a 2 in our subscript, we write out our CH3 group. And then how many CH2s do I draw? How many CH2 groups do I draw connected in my chain?
2.
2, yep. And we draw them as part of a straight chain because each of our carbons at the ends of our chain are completely saturated with hydrogen. So this would be the complete expanded structure for the following molecule. In organic, it's convention to write partially condensed structures whenever possible, rather than explicitly drawing out every single carbon-hydrogen bond. Does this make sense to everyone so far?
Yeah.
Perfect. So, I'd like you to take a moment and I'd like you to try and write the condensed formula for each structure. So what I'm going to do is I'm going to start us off and I'm going to do the first example, and then I'm going to also do the second example, and then you'll do a set. So in this first case, first I'm going to partially condense my structure. So I have CH3, CH2, 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 CH3. So I have 1, 2, 3, 4 CH2s. So I'm going to write this and condense this chain to CH3, CH2, and then what subscript do I put? What
4.
Yep, 4, yep. And then I write my CH3. So this would be my condensed structure. Now, there's something really cool that can be done with what are known as symmetrical structures. Does everyone notice how the left and right hand side of this molecule look identical, have the same number of carbons?
Yes.
Yeah. So for symmetrical molecules with a central atom that isn't carbon, what you can do is you can further condense and you can write out a highly condensed structure. Recognizing symmetry in organic chemistry will save you a lot of trouble. So this functionality is known as an ether, this ROR functionality. So for a generic ether, we'd write out our formula like so. So we have CH3, CH2, O, CH2, CH3. However, because these two chains are identical, we can simplify our structure and write it as O, CH2, CH3. And how many of these chains are attached to my oxygen? 2. This only works if they're identical. Does that make sense? So I'd like you to apply what you've learned. And I'd like you to tackle the following examples for dimethylamine, which again looks a little symmetrical to me, and the following alcohol, which would be known as 2-butanol. So I'd like you to try writing the condensed formulas for each of these structures in the chat, and then we'll discuss shortly. And we'll discuss this in about 2 to 3 minutes. And don't be shy to share your responses in the chat verbally or to type any questions into the chat as well. If you're ever unsure, don't be shy to ask a question. And we'll discuss in about another 2 minutes. Let's try to get some responses for both of these condensed formulas. So let's try to get a few more responses. And if you're unsure for providing your responses, don't be shy to ask a question and I'd be happy to clarify. So the structure that I see in the chat for 2-butanol, so you want to make sure that the attached functional group is written right after the carbon that functional group is attached to. So the ordering of atoms and functional groups in your condensed structure should reflect the ordering of atoms in your overall carbon chain. So let's try to get a few more responses and we'll discuss this example in about another minute. And it's good that we have a pool of responses in the chat. So let's discuss. So the majority, almost all the responses I saw for dimethylamine were perfectly correct. So we have NH, and then attached to our amine are two CH3 groups. Yep, that looks perfect. So for 2-butanol, so first, attached to our CH functionality, we put our attached groups that aren't part of our main chain in parentheses, and we write the formula. So we have CH3, CHOH, and then we write the rest of our chain, which would be CH2, CH3. So this is the condensed structure for 2-butanol, and we indicate this OH, this hydroxy or hydroxyl functionality is attached to this carbon by placing the hydroxyl functionality in parentheses and writing it immediately after the CH group. Does that make sense to everyone? So you put attached functional groups in parentheses right after the carbon it's attached to. Perfect. Let's keep doing a few more examples. So 2-butene, we have a carbon-carbon double bond. So that's a key signpost to remember. So this has an alkene functionality. So although 2-butene is symmetrical, we generally only invoke the symmetry shortcut when we have a central heteroatom. The way that you've written 2-butene, it's reflective of the way that it's reflective of the connectivity of the atoms, but in condensed formulas, we typically have to explicitly show that there is a double bond present. So we'd write this as CH3, CH, double bond, CH, CH3. And this is specifically for condensed structures where we have to show not only the fact that a carbon-carbon double bond is present, and the way that it was written in the chat is also perfectly fine. That's also perfectly fine. As long as you're noting the fact that these methyl groups are attached to these CH functional groups and that we have an alkene at the center of our molecule, that's all perfectly fine. So what I want everyone to do now is let's take about 1 to 2 minutes and let's try to write out the condensed formula for acetonitrile, which has a carbon-nitrogen triple bond with this functional group being known as a nitrile. It says so in the name even. So let's try to get some responses for the condensed formula for acetonitrile. Yep, the structure I see in the chat looks good. In general, in general, it's also perfectly reasonable if you have a double or triple bond, you can note it explicitly, or because the nitrile is a functional group, what you can do is you can abbreviate it with a formula for that functional group. So to discuss this example, because this nitrile is a defined functional group, acetonitrile is commonly written as CH3CN. Alternatively, you can explicitly showcase the double and triple bond as so. Both methods are common. In general, for functional groups, you'll be more likely to see this further condensed structure. And that's only because this CN is a defined functional group that we know the formula for. So when you're dealing with functional groups, be prepared when you're writing the condensed structures to, rather than explicitly writing out all of the double and triple bonds for your functional groups, just condensing your functional group into its representative formula. So you still write out your carbon-carbon double bonds and your carbon-carbon triple bonds, but for functional groups, you generally will see the functional group abbreviated further into just its representative formula. And we'll see that in this next example with acetaldehyde. So we have an aldehyde functionality. So this RCOH functionality is known as an aldehyde. And aldehydes are represented with the general formula RCHO. Aldehydes are represented by RCHO, while alcohols are represented by RCOH. So aldehydes have a unique condensed structure to explicitly note the fact that we have an aldehyde rather than an alcohol. So we write out our CH3 group, and then we condense our aldehyde by writing CHO. And this is a signpost we are dealing with an aldehyde. If we're looking at a partially condensed structure, so if we're looking at our partially condensed structure, it would look something like this. This is our partially condensed structure. So I'd like you to now try and write the formula for acetone and acetic acid, keeping in mind that acetone has what's known as a ketone functionality, which is written as CO. And acetic acid has what's known as a carboxylic acid functionality, which is written as RCO2H. So let's take about 2 to 3 minutes and let's try to write the condensed structures for each of the following molecules. And remember, if you have a symmetrical structure, it can be further simplified. And let's try to get a few more responses in the chat. And the responses I'm seeing so far look quite reasonable. If you're writing out acetone as if it's a long chain where your ketone's in the middle of the chain, you have to make sure you put the ketone oxygen in parentheses. So the responses we see in the chat look reasonable so far. So there are a few ways that we can write out the formula for acetone. So first and foremost, we can write out the formula for acetone as CH3COCH3. There is some debate over whether or not the oxygen needs to be put in parentheses. I find it's more explicit to denote you have a ketone rather than an ether. Another method, you can put the entire CO functionality in parentheses, though that is far less common. But because acetone is symmetrical, we can actually use another approach where we write this as CH3 to CO. In this case, we're noting that both of these CH3 groups are attached to our central carbon. So this would be a reasonable condensed formula for acetone. Acetic acid, thankfully, is an easy one. So let's look at acetic acid. So we'd abbreviate our CH3 group and we'd write our carboxylic acid as CO2H. So this is why it's really important to be familiar with the functional groups, and that's part of what the examples are trying to start to develop, a familiarity with the functional groups, because if you know the functional groups, you can write out their condensed formulas and you can write out their structural formulas more easily. Does that make sense to everyone? Do these examples make sense so far? Any questions? So we're going to keep going with this, and what we're going to do is we're now going to focus on drawing out Lewis structures. We're going to focus on drawing out Lewis structures. So if you may notice this little green button above your Zoom call, if you click on it, the green button, you'll see annotate features, and you'll see this little pen or a word called annotate. This gives you the option to draw on the whiteboard using your mouse or drawing tool. Just to check, if you look up in this little black bar up at the top called meeting options, is everyone able to find the annotate tool?
Yeah.
Okay, perfect. So that gives the option if you'd want to draw your proposed structure, you can share your proposed structure on the whiteboard. I'm going to do some representative examples. So we have 4 examples lined up on this page. I'm going to do the first 2, and the class will do the second 2. So first and foremost, I'm going to need everyone's help here. What is this arrangement of atoms? What functional group is indicated by this arrangement of atoms? ROR. What does that tell us?
It's an ether.
Yep, exactly right. So this functionality is known as an ether. Okay, perfect. That tells me a lot about how to draw out my overall formula and overall structure. So I'm going to write out my CH3, and working from left to right, I then write out a CH2. And based on my instruction manual, how many CH2s do I write out? 2, yep. Okay. Now, next on the list, we write out an oxygen and then our last CH3. So this would be our partially condensed formula. And of course, we can expand this out and explicitly draw out all of our carbon-hydrogen bonds. And that would in turn give us our complete Lewis structure for the following molecule. In this case, this would be methyl propyl ether. Does this first example make sense to everyone? Perfect. So in this second case, we have CH3CHO. So this CHO functionality is known as what functional group? CHO. What functional group does that remind everyone of?
Is it an aldehyde?
Yep, exactly right. So this is called an aldehyde. Okay, and it structurally looks like this. Perfect. So if we expand out our formula, we have CH3, COH. Yes, this is going to lead into line structures, and this is part of building up the idea of condensing our structures down so that we can eventually start to draw bond line structures. So if we're explicitly writing out each of our carbon-hydrogen bonds and all of our lone pairs, the full Lewis structure for methyl aldehyde is shown here. So now that we've seen some examples, I'd like the class to work on the following two problems. And I'd like the class to not only assign the functional groups found in each molecule, but to write out a full Lewis structure for each of these molecules. So start by going from the condensed structure to a partially condensed to a full Lewis structure. And don't be shy to share your responses using the annotate tool. There's plenty of space. And don't worry, different students have different pen colors, but and whatever structure is written out, I'd be happy to provide feedback. Otherwise, one way that if you want to use other tools besides the annotate feature, you can focus on identifying the functional groups in each of these molecules and communicating that in the chat as well. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to draw your proposed structure using the annotate feature, or to type out the functional groups found in each of the molecules into the chat, or to state it verbally. Any place where I can provide feedback. And if you have any questions, again, don't be shy to type them in the chat or to unmute and ask them verbally. Yep, exactly right. That structure looks perfect. Let's try to get some responses for the second structure. And don't be shy to share your proposed response. Any structure that's proposed really helps give me a sense of how students are processing the information and how I can best phrase and present other examples to help clarify. So the first molecule, it doesn't quite have a carboxylic acid, which is of the form RCO2H. Instead, we see an OH functionality, which is known as an alcohol. For the second structure, the students in the chat are very correct in noting that we do have an alkene functionality. Would someone like to draw out the proposed partially condensed structure for this second molecule? And really don't be shy. The proposed structures really help facilitate this discussion. And again, you can access the pen by going to the top little black bar for the meeting controls and clicking annotate. You're on the right track. You're on the right track. So to pick up on the student responses, allow me to clear and let's first write out for the first example. But thank you for sharing. That was actually it was on the right track. I think it was you just accidentally erased it because you were almost there actually. So for the following structure, the main hallmark, the main sort of red flag is the fact this carbon has no hydrogens, which means everything is likely going to be attached to this carbon. So we draw our carbon, attached to it are 2 of our methyl groups, and then 2 of our hydroxyl groups. This OH is known as an alcohol or a hydroxyl group. Does this make sense to everyone? Does this first structure make sense? Perfect. So to pick up, looking at this second structure, again, we have a carbon with no hydrogen. So we likely have a bunch of things attached to it. So I'm going to draw my carbon-carbon double bond and then attach to this carbon, as your classmate has drawn in their shared example, we have a CH2CH3 group. We have an ethyl group. And how many ethyl groups do we have? How many of these groups do we have? 2. So all we have to do is just draw a second ethyl group. And this gives us a valid structure for the following molecule. Does this make sense to everyone? Is everyone comfortable with these examples?
Professor, for the first one,
Yes.
can you put hydroxide on the top and bottom?
It actually doesn't matter where you put it because this structure is symmetrical. So no matter how you arrange it, you could just as easily draw it like this. These 2 structures are actually the same via rotation.
Okay, because that's how I wrote it.
Yep, and that would be perfectly fine. Yep.
Thank you.
Mm-hmm. So, one moment, give it 1 second. Okay, so let's now talk about drawing constitutional isomers efficiently. So this is the thought process I like to use when drawing constitutional isomers. A fast way to draw constitutional isomers is by changing the connectivity and position of functional groups and atoms in our molecule. The fastest way to generate a constitutional isomer, as we talked about earlier, is to swap a functional group or carbon chain on one carbon with a hydrogen on the other. So first, you number your carbons, and I like to use two different colors, one for left to right, and the other from right to left. And the trick is you can swap your functional group and a hydrogen if they have different numbers for both counting methods. Okay. Now, you may ask, why does this method actually work? Well, the reason why you count in two directions is that a constitutional isomer by definition has different connectivity. If you can rotate your molecule to give the same structure, the structure is not a constitutional isomer. If a functional group has the same carbon number, the connectivity has not changed. Now, this is a common problem motif in organic chemistry. So for example, I know this is going to seem a little bit silly at first, but bear with me. So if we compare this first structure to the following second structure, are these two structures the same or different? Are these two structures the same or different?
They're the same.
They're the same. And to prove this, let's look at what happens when we number our carbons. So in general, you want to have your numbering convention so that the carbon with the same functional group gets the same number. So 1, 2, 3, 4.
Doesn't this like kind of lead into the skeletal like line, well, the line structures?
Yes,
Because
exactly.
like 1, 2 methyl whatever.
Yeah,
Kinda
it
goes
it also leads into and begins to develop the rules for naming compounds as well. That's part of the scaffolding associated with this method. Exactly right. So, as we can notice, if we look at the carbon attached to our alcohol, is the number the same or different? It's the same. And the number is the same for all of our other carbons as well. So these two structures are just rotated versions of each other. To show how we'd actually generate a constitutional isomer, so I'm going to write out and just explicitly draw one of my hydrogens for each of these carbons. I know it seems like a bit of an odd way of drawing. Okay, so based on this rule, we're going to number this molecule from left to right and right to left. So we can swap any functional group or carbon and any hydrogen if the number in blue and red are different. So what do I mean by that? So I can swap, for example, this hydrogen with this carbon. Why? If we check the numbers, are the numbers in blue and red the same or different?
Different.
Different. To showcase an example that doesn't work, we can't swap the carbon. We can't swap the carbon here. So to show an example where it doesn't work, let's first show the example that does and the result, just so we can see what we've gotten. So if we swap these two functionalities, we get CH2, well, CH2, now it's attached to a hydrogen, CH, CH3, CH2, OH. And as we notice, if we number and we look at our carbon numbering, does everyone notice how carbon 2 now has a different set of atoms attached to it? Does everyone notice how carbon 2 now has this methyl group, this CH3 group attached to it? So this would be a valid constitutional isomer. Now, you can also get a little bit creative here. You can also get a little bit creative here. And if you number, including your oxygen atom, you can generate some more complicated structures. So, for example, we cannot swap, so I'm going to just put an X. We can't swap our oxygen and our carbon at the end because they have the same number. Does everyone see how the oxygen and carbon have the same number in this method? So as a result, they can't be swapped. What we can do, however, is we can swap the hydrogen on our oxygen with the carbon. We can swap the hydrogen and we can generate a structure with an entirely different functional group. So in one example of a constitutional isomer, so we have CH3, CH2, CH2, O, CH3. So in this case, we've generated an entirely new arrangement of atoms by swapping a hydrogen and our carbon. Now, this is just a method of approximation. I do want you to be familiar with numbering your carbon because that will tell you immediately whether or not your structure are constitutional isomers or if your structures are in fact identical. You are welcome to draw your constitutional isomers using whatever method you prefer. Does this make sense to everyone? Does this idea make sense to everyone?
So we pretty much just swap the hydrogen from our functional group to another carbon?
Yep. Or you can even move your functional group.
Okay.
Mm-hmm. So, just to showcase and to build on this idea, you can also draw constitutional isomers by exchanging a carbon chain with a hydrogen atom or a functional group. So in this case, you number your carbons and non-hydrogen atoms, and you can swap your carbon chain and hydrogens if you have two different numbers. So just to show an example of this, if we have CH3, CH2, CH2, CH2OH, and if we number all of our atoms, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we can swap this methyl group. We can swap this methyl group with the hydrogen on carbon number 3. And that in turn would give us the following constitutional isomer. We have CH3, CH, CH3, CH2OH. So this would be a valid constitutional isomer. Now, what's also pretty cool is that you can also exchange your non-hydrogen atoms as well. So to showcase the application of that, so if we have CH3, CH2, CH2, CH2OH, if we number our atoms, we can just as easily swap this carbon. We can just as easily swap this carbon with our oxygen. So if we do that, we end up with the following constitutional isomer. So you can either swap portions of your carbon chain, or you can swap a hydrogen atom with a functional group or carbon atom. This is just a very procedural way of writing constitutional isomers. You'll eventually develop methods to write constitutional isomers more by feel. So, as our last example for this first session portion, I'd like you to try drawing as many constitutional isomers as possible for the following formula: CH3, CH2, NH2. And to help you with this, I'm going to teach you a little trick where when you look at a formula, you can calculate what is known as degree of unsaturation. And essentially what this does is it compares our ideal case, our ideal formula, to our actual formula. So ideally, for example, a carbon chain has the form CnHn plus HN plus 2. If we add an amine functional group, we are replacing a hydrogen with an NH2 functionality. So for our ideal amine, we have the formula CnH. So CnH and then N plus 3N. So this is our ideal formula, and we compare it to our actual formula. So to calculate du, you take the number of carbons, and you may ask, what's the purpose of du? Du allows you to calculate the number of double bonds or rings. So the du formula, if we're expanding it out, is equal to the number of carbons minus the number of hydrogens over 2 plus the number of nitrogens over 2 plus 1. So to show how this du formula works, we have 2 carbons. We have 1, 2, 3, 4, 5, 6, 7. So we have 7 hydrogens over 2. We have 1 nitrogen over 2. And then we have plus 1. Okay? So we have 3 minus 6 over 2, which gives us a du value of 0. So this tells us we have no double bonds. So du allows you to very quickly see whether or not we have double bonds or rings. So this is a formula that you'll want to be familiar with, and that I'm showing you this now because if you choose to use it, it gives you a nice way of minimizing and reducing your options. So with that established, now that we know this structure has no double bonds or rings, I'd like you to draw as many constitutional isomers as possible for this. So I'd like you to draw as many constitutional isomers as possible for this structure. And don't be shy to break out the annotate tool to draw out your constitutional isomers. What you can also do is you can type in the chat the proposed condensed formula for each constitutional isomer. So all of these DU calculations that we did at the start are just to tell us we have no double bonds. And that allows us to simplify how many structures we draw. So let's try to get some shared responses in the chat. This will be the last example for today before we close out this lecture session. But I want to make sure that everyone can at least draw some constitutional isomers for this representative example. And don't be shy to share your responses in the chat for your proposed constitutional isomers. You can either draw them out with the annotate tool, you can write the condensed formulas in chat, or you can ask a question. And either way, I'd be happy to provide feedback. And don't be shy while one of your classmates is drawing to draw another structure on the side. There's plenty of whiteboard space. That looks great. That's one of our constitutional isomers. Exactly right. Would someone like to share the second constitutional isomer? And don't be shy. We only have one other constitutional isomer to draw. And don't be shy, you can also type the condensed formula for the other constitutional isomer in the chat. Yep, that looks perfect. So these are the two possible constitutional isomers. So let's clear these annotations and then I'll provide the instructor solution. So the first structure we're going to draw is just straight from our condensed structure. We're just going to draw out straight from our condensed structure our first Lewis structure. Okay, now if we number if we number our atoms, okay, so now what we can do is we can swap this hydrogen. We can swap this hydrogen with this entire functional group. The reason why this works is nitrogen has number 3, while the carbon attached to this methyl group has carbon 2. So this swap is okay. So now what we're going to do is we're going to draw out our constitutional isomer. So we have a CH3 group now because we replaced this methyl group with a hydrogen. We have our amine, and then we have our second CH3. So these are our 2 constitutional isomers. Does this example make sense to everyone? You don't have to use the numbering method if you don't like it. This is just different sets of tools you can use. Whatever you're comfortable with, that's what you should try and use. So we'll pause the recording for today.